the roll yet. It's going to take a while. The Marcus is here. Clark's here. Pour me out. Okay. Okay. Goodness gracious, man. Thank you. Does the room feel cool to y'all? Yeah. Huh?
It is a little cool.
It was this way Monday, and I called them and they did something, got it running. Student in my other class, there was absolutely no heat coming out of here at all. She said the ventilation had come on. I don't think it had. Now, I don't need this, okay? Let's see, is there anything that we need to discuss? I know we did this problem.
We did. Exactly 5 last.
Yeah, we did 5. Yeah, but I was trying to find some, yeah, I think this is what I had to use to write on. Here's example 6. I'm sorry. My head is just completely clogged up. All right. Find the centroid of a region shown in a figure that they don't show us. Okay. Boo hiss. Okay. And by the way, there's absolutely no calculus involved with this at all. It's just talking about centroids. So let me do my best to draw this.
We both have a book, too.
Oh, you both have books, yeah. Okay, so you got it to look at it. All right. Now, well, I still almost need to draw it to talk through it. And here's Catherine. Okay. It's 1 unit across here, 3 units down, 2 units down here, 3 units across here, 1 unit up here, 2 units across there, 2 units down here, and then connect at the bottom. Okay, so this is 1, 3, 2, 3, 2, 2, and that would make it 6 here, I think. Is that your interpretation of this? This would be a 1 there. Okay. It says find the centroid of the region shown in this. Okay. Now, they call it a lamina. Okay. And I guess I should have made that a dotted line. So let me erase that and dot that in. And dot this in. Okay. Now, because it's a lamina, it's uniform density, right? So therefore, really, the center of that is the center of gravity, you might say. So that'd be with this being the y-axis and that being the x-axis, okay? Then this would be at 1/2 is your x-coordinate here, and 3/2 is your y-coordinate. You buy that? That point right there. Halfway between there and there is 1/2, and halfway between 1 and 3 is 3 halves. So that's the center of mass of that little portion. All right. The center of mass of this one is, now, this is 1, 2, 3, 4, okay? Get out of there, okay. So the center of mass of this one is right here, which would be 2.5, so that would be 5 halves, and 1/2 is the Y. Would you buy that? Okay, yeah, that's what they got too. And then the center of mass for this one is right here at 5, 1. Yeah, that's what they got too. All right, good deal. Now, those are the centers of mass for those blocks, and then what you can do is, this is the way they do these things, you can treat this whole block as this mass right there, this whole block is this mass right there, and this whole block is this mass right there. Now, the trouble is, a lamina is uniform density, but this has an area of 3 by 1, so this is 3. This has an area of 3 by 1, so that's 3. This has an area of 2 by 2, so that's 4. Okay, so you see they're not the same masses there. So you can count this mass as being 3, 3, and 4. Okay, so what you do then to get the center of mass of the whole thing, and by the way, do any of you have a prediction of where the center of mass of this thing is going to be?
7 halves.
Okay. My gut feeling, it's not even going to be in the block itself. It's going to be somewhere, I'm guessing somewhere around in here.
I thought it had to be in the.
Huh?
I thought it had to be in the figure.
No, that's the deal. That's why I asked that. You would think it had to be, but the center of mass really doesn't. Okay? Just picture this as a weird example. Let's say you have a ring. Okay? The center of mass is right there, but there's nothing there. You know, the ring is here. So this is, I'm guessing that. I may be wrong, but there's enough elevated here. I think it's got to be somewhere in between here and here, and there's enough mass up here that I think is going to pull it somewhere up in here. Maybe not. It might be right near the line. I don't know. We'll see. Okay? So, yeah.
Explains it for me because on the x-axis of the cube on the right side, it's not a cube but like a square. Why is it 5 for the x-axis instead of like 1? Because I would have thought that 1 would make like the
Okay. I didn't understand all that.
Why is it 5 instead of 1?
Where? This?
Yes.
Okay, where the point where those masses are. You see, this is a square right here, 2 by 2.
Yes.
Okay, so the middle of this square is 1 in from here and 1 up from there, right? Okay, but this is 1, 2, 3, 4, 5, 6. There's the 6 along here. So this is the 5, 1. At the coordinate 5, 1. Now, when we talk about center of mass, it's relative to the origin. Okay, that's what we're doing about. Okay, so to get the center of mass of the thing, we do, and I remember we said the mass of this one, M1 is 3, M2 is also 3, and M3 is 4. Okay, just so you know that. We're just assuming a density of 1, and this has an area of 3 by 1 is 3, so that would have a density of 1 unit of mass per area, and the area is 3, so that would be a mass of 3. Again, 1 by 3 is 3, and then 2 by 2 is 4. Okay. So your X bar, remember, is your moment with respect to the y-axis, basically. So that would be for the first one, it's X displacement is 1/2 times 3 plus 5/2 times 3 plus 5 times 4 divided by the total mass, 10. Okay, because we said the total mass is 3 plus 3 plus 4. That would be 10. Okay, so you have to do your calculations here. That would be 3/2 plus 15/2 plus 40/2. We don't need to do that. Let's just leave it as 20. I was going to make it clever and do that, but we add those two together, and that gives you 18/2, which is 9. So it's 29 over 10, which is 2.9. Okay, your y bar is going to be from the x-axis, so that's going to be 3/2 times 3 plus 1/2, the y coordinates here, times 3 plus 1/4. Okay? And that's going to be 9/2 plus 3/2 plus 4. That's 12/2, which is 6, plus 4 is 10. 10 over 10, because you divide by the total mass, and that's going to be 1. Okay, so it is going to be right on the boundary. 2.9, 1, 2, almost 3, right there. There's the center of mass. Right on the boundary. Not quite outside, but not quite inside either. Right on the boundary. Straddling the fence. Okay. So the key here is when you have a lamina, everything's uniform. Okay. Then you can treat each portion as if it's a point mass. Okay. That all of the mass of this region is located right at its center of gravity. That's its center of gravity. That's its center of gravity, and then go from there. Otherwise, it would be a real pain in the neck. It's already a big enough pain in the neck, but that's what it is. So if it is a lamina, which they said it was, then uniform density, you know that its center of mass will be its midpoint, midpoint, midpoint. Just calculating what those are. These are easy enough numbers. You could do that, just picking them out, and then use that to come up with the location of the center of mass. It would be a point 2.9, comma 1. Short of 3, comma 1. Any questions on that? Does that make sense? No calculus involved with it at all. Just basically the definition. First, figuring out what the center of mass of each one is, then assuming all the mass is located at that point, and then using that to do your center of mass for the whole figure. Okay. Understanding they have different masses, because those first two are area 3, the last one was area 4, so they would have different masses. If they were all the same masses, you wouldn't even have to worry about the mass, but you do on this one because they are different. First two are the same. The third one's different. All right. Any questions on it? Does it make sense? And I think when you get in your statics and dynamics in your engineering school, you'll be doing this kind of thing probably a lot. I wasn't an engineer, so I didn't take statics and dynamics, but I've talked with enough people who did that seems to be the kind of stuff they do. All right, any questions? So let's move on to, and this again is, you still need it a little bit longer.
I can probably get it. I was trying to write down my figure. I'm good
What's that?
I'm finished.
Yeah, okay. What we're going to do is move on to the theorem of Pappus. Sort of an interesting little thing. Final topic in this section is a useful theorem credited to Pappus of Alexandria. And in case you were wondering, Alexandria was, you see a lot of things of Alexandria. That was the center of knowledge for at least the Western world for probably several centuries, maybe even millennia or so. It was in Egypt, Alexandria, Egypt, and Egypt was one of the earliest civilizations. And Alexandria may have one time, I imagine it was the capital of Egypt, but then even when it moved, there was a great library at Alexandria. It was people from everywhere came to Alexandria to learn. The Persians, Babylonians, Greeks, the Egyptians, of course, Europeans that were smart enough to do it, they went there. Europeans were rather barbaric back then, so this is before they were very well civilized, but everyone went there. So there was, the great library was there. Now,
And then, it doesn't have to do with Alexander the Great.
you mean the name of it?
Oh, there was like several Alexandrias at the time, and it was all where he had gone around and
Okay.
popped
My-
up cities.
My concept of it, and I may be wrong on this, I'm trying to piece together a timeline here. Alexander the Great was trying to piece together the timeline for him. He certainly was before the Roman Empire. So I was thinking Alexandria was there before he was there, but I'm not absolutely certain on that. But see, Alexandria was there for a long, long time now. This guy that we're talking about here was 300 AD, so he's after the birth of Christ. So that's much later. What I was going to get at was the reason Alexandria is not the great center of learning it is now, unfortunately, I think it had to do with one of the Crusades. Because by the time of the Crusades, the Egypt and the others had fallen into the Muslim influence. And they were very bright people but when the Christians from Europe typically weren't all that bright, because the ones doing the fighting were fairly close to illiterate serfs. And I think they must have had a commander who was sort of a zealot and said, "Oh, this is pagan stuff, burn it to the ground." And they basically took that great, incredible library of Alexandria and burned everything they could get their hands on. And there went centuries of knowledge up in smoke. Fortunately, people had copied things from there, and taken. Second?
I was going to ask, were there no Baptists? Because I have heard stories where people who must take their transcripts, copied it, and sent it to Alexandria. But
Right.
were there no like an official backup of that Alexandria?
Well, remember, everything was done by hand, and people had gone in there and handwritten and copied things like that from there and taken it back home with them, Persia or Babylon or wherever it was, Greece or wherever. So there was, all the knowledge wasn't lost, but that great library was basically decimated, and not knowing what they were destroying, because they probably were illiterate themselves. But I shouldn't have gotten off onto that.
But this does say it was named for Alexander the Great
Oh, really?
in April of 331 BC.
Okay. But that wasn't when the town was formed, was it? Was it just renamed? I think that's what it was. I think the city was there probably under an Egyptian name, and when he conquered it, and he had enough sense not to destroy the library, they renamed the city after him. So that makes sense if it said name for him. So but you may be right. That may be when it was formed. I don't know.
Well, that didn't say that.
Yeah. Okay. But that makes sense, because why else would you name a city in Egypt Alexandria? That's not an Egyptian word, So, all right. And Daniel's here.
And he was the one that married Cleopatra. Was it Alexandrian Great?
No, she was more the time of the Caesars, because I think, again, check me up on that one too, because I think it was Mark Antony married her.
Yeah, I think that is right.
Yeah, okay. And he was one who either supported or, I don't know, there was all the political intrigue back then. He was one of the three. They had the triumvirate or something like that followed Caesar. He was one of the three, and then somebody grew more powerful. I don't know. It was a mess. I don't know my history that well. But anyway, the final topic is this, and here's what the theorem of Pappus says. Let R be a region in a plane, and let L be a line in the same plane, such that L does not intersect the interior of R. Okay? As shown in this figure. So here's the plane, this purple sheet that goes through there, and L is a line in the plane, but it doesn't intersect the interior of R. That's not really making a lot of sense. Let R be a region in a plane, and let L be a line in the same plane, such that L does not intersect the interior of R. So I think what they're talking about, the region you're talking about is here in a plane, but it's not the entire plane, it's just some region here. It could have been there or here. I think it's here. And L is not, it's in the plane that's in, but it's not in that region, but it's in the same plane as the region. Okay. If little r, now that's capital R, the region. If little r is the distance between the centroid of that, so yeah, here's that r, I didn't see it. Capital R down here is this little rectangle in a plane. L is in the same plane as that rectangle, but not in the rectangle. Okay. And if R is the distance between the centroid of R and that line L, then the volume V of the solid of revolution formed by revolving this region around the line is V is equal to 2 pi R times A. What's A? A is the area of this region that you started with. Okay? So the volume that's made by that. Now, the thing that confuses me about this figure here, okay, let me backtrack and redo part of what I said. The plane is the purple, okay? I backed off of that and said it wasn't. No, the plane is the purple region. That's flat, okay? The region R in the plane is this orange part here, just the orange part of that plane. L is in the same plane, but not in the orange part, okay? So, therefore, this region is here. If you take this region and revolve it around that line that's not in the region, then the volume that you make of that cylinder, okay, pipe, whatever you want to call that, is 2 pi R, which is 2 pi times the radius of that centroid. That's the area that gets revolved around. I mean, that's the circumference that gets revolved around 2 pi R times the area of this. That will give you the volume here. Now, there's a part of me that says that shouldn't be, because This part out here travels further than the part in there, but that's what the centroid does. It's sort of the average of all that, and if it goes around, that gives you that. It's a real handy shortcut for doing that. Where A is the area of that region R, okay? 2 pi r is the distance traveled by the centroid as the region is revolved around the line. So that's the theorem of Pappus. He probably used calculus to derive that, perhaps. No, he wouldn't have used calculus because calculus hadn't been invented by then, but his thought processes were there. These are long before calculus, okay? Now, the theorem of Pappus can be used to find the volume of a torus, and that's not a car, that is spelled differently. As shown in the next example, a torus is a donut-shaped solid formed by revolving a circular region about a line that lies in the same plane as the circle but does not intersect the circle. Okay? So basically, donut's the best way I can think of doing it, picturing it. It's a circle going around the line that doesn't intersect the circle. Okay? And that's what this example is. Find the volume of the torus shown here, which is formed by revolving the circular region bounded by, okay, this is a circle, by the way. X minus 2 squared plus y squared is equal to 1. This places the center of the circle at x equal 2 out here. Y is equal to 0, so it's on the x-axis, and then a radius of 1, if you remember your thing for a circle. So the radius of 1 doesn't touch, this radius of 1 here centered at 2, doesn't touch the x-axis, the y-axis, which is your, you don't really say what it's revolved around, but, about the y-axis. Okay, about the y-axis, so it doesn't touch that. So you want the volume of that? Well, the area of this is pi r squared, but the radius of, the centroid here is at 2, 0, the center of the circle, 2, 0. Okay? The area of this circle has a radius. This circle has a radius of 1, because from right here and right here. That circle has a radius of 1. So this is just pi. Pi times r squared, r is 1. So this is pi, is the area of that circle. Okay? And then it's 2 pi r, where r is 2, because that's the distance from the center, the axis of symmetry, the y-axis, and the center of that, the centroid is 2. So 2 pi r, that r being this 2, not the r of the circle. There's too many r's here, okay? So 2 pi r times the area, which is pi, that's 2 times 2, 4 times pi squared. Pi times pi is pi squared. So it's 2 squared times pi squared, 2 or 4 pi squared. Okay? Again, doing no calculus, but using that you found that everything through calculus. So let's see. You can see that the centroid of the circular region is 2, 0. I hope you can see that, right? This circular region here has a center at 2, 0. Okay, right there is the center. Okay? And that circular region, if it's a lamina, which we assume it is, part of the circular region, it's just a region. Okay? May not even have any density to it, but it's just this region here. Then the radius would be the center, from 0 to 2. Okay? All right, see that the centroid is at 2, 0. Okay? So the distance between the centroid and the axis is r is equal to 2, because that's where the centroid is. And x equals 0 is where the y-axis is. Okay, so your 2 pi RA would be 2 times pi times the radius, which is another 2, and because the area of the circular region is pi, because its little radius is 1, and its area is pi r squared, pi times 1 squared is pi, so you have 4 pi squared. 2 pi times 2 times pi, 4 pi squared. All right. Which is, if you wanted to figure that out, and this is just an approximation I always use, as I always think of pi squared as being awfully close to 10. Not exactly 10, but it's really close to it. Do that on a calculator and see how close it is.
9.86.
Yeah, so it's really, really pretty close. So that's close to 4 times 10, close to 40, 39.5. Okay, that's pretty close. All right. You may have use of doing that someday in the future. I don't know. Homework exercises here include either 5 or 7 or both. They're both at Calc Chat. 7's at Calc View. Do number 9, it's at Calc Chat. Do either 11 or 13 or both. They're both at Calc Chat. 11's at Calc View. Do any of the odds 15 to 27. They're all at Calc Chat. 15's at Calc View. Do 29. Do either 31 or 33. They're both at Calc Chat. 33's at Calc View. Do 35, it's at Calc Chat. 37 or 39, they're both at Calc Chat. 37's at Calc View. And again, like I said before, you can explore doing 41 or 43 if you like. They should both be at Calc Chat. Any of the odds 45 to 49, they're all at Calc Chat. Then any of the odds either 51 or 53, they're both at Calc Chat. I think we had all those before. Now the only new thing we've got is either 55 is using theorem of Pappus, and then 57 if I'm not mistaken, is sort of doing it backwards, but you have to read through it and see. Only if you're interested in doing that. All right, let's move on to 7.7. Goodness gracious, my head is so clogged up. I wish I'd have called this morning. This is the last section in the chapter, and so we finish it. And yeah, and this is a real short section. Let's second.
I think it's short.
Yeah, so let's hopefully we'll finish it today. Now, I was saying earlier, my sad, sad song, that I got such an enormous series of interruptions yesterday. I didn't get to make, I think I've got your test made out on Chapter 7, but I didn't get to run it off. Let me verify that quickly. This would be Chapter 7. Oh, man, my head. Why am I not? Ah, here. This may be it. Why am I not finding it? may have. That was the test I gave y'all. Here we go. I think I found it. Yeah. Yeah. Let's see if I have it run off. Yes. Got 1, 2. Only got 2 run off. I'm going to have to go make more copies, but if you have to leave early, be sure you get one before you go. Bless you. When do you have to leave?
Like probably 10 or 15 minutes.
Okay, before you go. That's what I wanted to make sure. Sorry it took so long to find it. But I do have 2 run off. I've got to run off more for the rest of them. Okay. So this is still Chapter 7, Applications of Integration. Fluids, pressures, and fluid forces. The objective is to find fluid pressure and fluid force. Okay. Pressure is defined, this is definition, a little bit of physics here, force per unit area over the surface of a body. In general, the pressure is proportional to the depth of the object in the fluid. So we're talking about fluid pressures, fluid forces. Okay? So here's the definition. Pressure P, capital P, on an object at a depth h, at a given depth h, in a liquid is P is equal to W times H. What is W? W is the weight density of the liquid per unit volume. Volume, okay? Nope. Excuse me. Why volume here? Remember, pressure is force per unit area, okay? And weight density would be mass per unit volume, and multiply that by the depth, and you get mass per unit area. Okay, so that's how you get pressure, or force per unit area. I'm sorry, not mass, force per unit area. And I think under all that is Vince, right? That's right. All right. Now, here are some common weight densities of fluids in pounds per cubic feet, which are unusual that they would give this. Normally we'd be doing Newton per cubic meter. They're using pound per cubic feet. Ethyl alcohol, 4.9 pounds per cubic feet. Gasoline, less than that, 41.0 to 43.0. Glycerin, much denser than that. That would be 78.6 pounds per cubic feet. More dense than water is. A lot more dense than alcohol and gasoline. Kerosene, kind of more dense than ethyl alcohol or gasoline. A little more dense than that. Mercury, look at that. 849. I mean, the rest of them are in the 50 to 70 range, 50 to 80 range, and it's 849. It's the densest liquid at normal temperatures and pressures that we know of. Seawater just a little bit denser than freshwater. Freshwater 62.4 pounds per cubic feet. You don't need to know those, just know where to look them up when you're working your problems, and that's why they gave them to you. All right. When calculating fluid pressure, you use an important physical law called Pascal's principle, named after the French mathematician Blaise Pascal. Now, he's not just a mathematician, he was also a pretty good physicist himself. The Pascal principle states that the pressure exerted by a fluid at a depth h is transmitted equally in all directions. Okay? So if you have, this is a body of fluid here, a clear tank, you might say. Okay? If you go down a certain depth here, If your solid down there is basically horizontal, the pressure is the same throughout. If it's sitting vertically like this, the pressure right here is the same as here, but it's not the same down here or up there because those are different heights. But at this height, the pressure is equal no matter how the thing is. It could be a face this way, that way, this way, slant, or whatever. At any given depth, the pressure is always the same. Okay? That was basically Pascal's principle. Okay? So in this figure, the pressure indicated depth is the same for all three objects at that point. Okay, certainly this object has things at greater pressures here, lesser pressure there, this is greater pressure here, lesser pressure there. But at that point, all the pressures are the same, no matter which. Now, here's another thing. If you have a planar surface here, the pressure is always perpendicular to the plane. That's why this one at an angle like this, the pressure is perpendicular to that. Okay. They do in the book a little bit of a blurb on Blaise Pascal. He highly influenced Leibniz, and I think he came along a little bit before Leibniz and was a great influence on him, but a lot of the things he did, Leibniz used to develop calculus. Okay. Now, remember on this slide, I said it's unusual they're doing pounds per cubic feet. I said you would think they'd use newtons per cubic meter, right? That's the SI unit. Well, guess what a newton per cubic meter is called? Pascal. They named the unit after him. But because I already had a P unit somewhere, his abbreviation is PA. Have you ever seen that abbreviation PA anywhere? On the sidewall of your tires. Because when you talk about the air pressure inside, they used to say just PSI when everything was done in American terms. That's pounds per square inch. This is pounds per cubic foot. Okay. No, these are weight densities. I'm sorry. That's not what I meant. These, when you multiply by the depth, that would give you pressure in pounds per square foot. And that's what I was going to say. Normally we use pounds per square inch. But in the SI unit, it is newtons per square meter, which is a Pascal. Okay. So on the sidewalls of your tire, you won't see PA by itself, you'll see kPa, because a Pascal of pressure is so incredibly small. A newton's less than a pound, so that's small itself, but when you spread a newton over a square meter, which is basically, if you picture that door there from the doorknob to the floor, that's about a square meter. That's a huge area over which to divide into a single little newton. So a Pascal, if I were to go and open the door, that would change the pressure in the room by several pascals. Did you notice it? Not at all. Your ears didn't pop, did they? No. Okay. So a few psi is equivalent to so many kPa, thousands of Pascal. So kPa, I'm sorry, not kPa. All right, but anyway, let's go back to this. All right. Because fluid pressure is given in terms of force per unit area, of course, the fluid force on submerged horizontal surface is force is equal to pressure times area. So since the pressure is force divided by area, newtons per square meter, pounds per square inch, pounds per square foot, whatever, then to get the force, you multiply the pressure times the area. Pressure pounds per square inch times square inches, okay, or pounds per cubic foot by square feet by square feet, pounds per square meter by the number of square meters. So that gives, or newton per square meter, okay. So find the fluid force on the rectangular metal sheet measuring 3 feet by 4 feet, submerged in 6 feet of water, as shown in this figure. Okay. Now, okay, here's the sheet of metal. I was trying to find it. I was looking for it this way. I thought that gray area there was it. I said, this is going to be a tough problem. No, the sheet of metal is down here, 3 feet by 4 feet. Yeah. Submerged flat in this tank of water. Okay. Number one, 6 feet of water. So from the surface down here is 6 feet. Okay. And it's 3 feet by 4 feet. So its area is 12 square feet. Okay. Find the fluid force. And we just said it's on the previous slide, so I'm going to have to do it here. The force is equal to pressure times area, right? Pounds per square foot times square feet. Okay? Now, earlier, they gave us what pressure was. Pressure is equal to the weight density times the depth. So to extend this formula, that would be the weight density times depth times the area, right? Well, the weight density of water they gave us earlier, and we assume this is fresh water, not salt water, seawater. So that's 62.4 pounds per cubic foot times the depth is 6 feet times the area was 12 square feet. 3 feet by 4 feet. The area is 12 square feet. Okay? Pull out your handy dandy calculators and figure out what that is. 62.4, and notice here, feet times square feet is cubic feet. Those cancel out. So this will be the total force on that plate. 62.4 times 6 times 12. Ugh. Basically 72 by 62.4. Something on the order of 500, something close to that, pounds. No, 5,000. 4,500, something like that. Anyone got it?
I got 4,492.
4,492.8. Let's just round that to about 4,500 pounds. Okay, that was my guess anyway. They probably carry a few more digits here. Oh, they do the 4492.8. They carry them all. Now, I don't know if this would come as a surprise. If that was a tank of water, that would be the force, fluid force on that plate. If this was in a swimming pool, and it was just down there at a depth of 6 feet, same. If it was in the Great Lake, well, not the Great, in the Great Lake, the freshwater lake, submerged. It doesn't matter what the container is, it's what the depth of the water is and the density of the water. Okay? That's all that matters on that plate of a given size. Now, let's see if they have another slide here. Oh, here's they're going to show how they did it. Because the weight density of water is 62.4 pounds per cubic feet, the sheet is submerged 6 feet of water. The fluid pressure is 62.4 times 6, which is 374.4 pounds per square foot. That's the pressure, and multiply that by the area, and that's where you get 4492.8. And that result is independent of the size of the body of water. The fluid force would be the same. A swimming pool, a lake, a tank, whatever it was in, as long as it was 6 feet down and horizontal. So here's the definition of force exerted by a fluid. This is the very bottom. So they do leave out what they're saying here. So let me read this. In example 1, the fact that the sheet is rectangular and horizontal means that you do not need the methods of calculus to solve the problem. Notice we didn't use any calculus, we just calculated. Consider a surface that is submerged vertically in a fluid. That's a lot more difficult because now you have to split, because it's at depth, that's what matters. So you have to do little strips that are at the same depth. That's where calculus is going to come into play. Okay? All right. Now, because they're going to do, before we get to the next slide, they introduce in this paragraph here a bunch of the terms they use in the next slide. So that's why I wanted to come back and do it. So what you do is divide the, if you have a material there that's submerged vertically, divide it into delta y's, because at a given depth, the pressure is always the same. So you do delta y now, where y is the depth. Okay. Consider a representative rectangle, and the length of that rectangle goodness, I'm having trouble breathing. Is some L of that depth. Now, if it's a rectangle, it's not a function of depth, it's just there. But if it's an odd-shaped thing, then any rectangular strip would be dependent on how deep it is, because if it's changing with depth, then that would be. So that's why they introduced that concept in here, L of y. That's the length of that strip. You have a delta y is the width of the strip, L is the length of the strip, and then your weight density goes in front of it. Weight density times depth times that area. So that's what they're heading toward, and then this is what it comes out to. But you see, they just threw this in here without that previous paragraph. You wouldn't know what these things were. All right, so the force exerted by a fluid of constant weight density. The fluid is constant weight density, and that's W. That's unit weight per unit volume. Against a submerged vertical plane region from y is equal to c to y is equal to d. So the top part is at depth c, the bottom part is depth d. Okay? So the force, the total force on that would be the weight density, assuming that's uniform, times the limit as your partition is going to 0 of the summation of all those partitions. Okay? Now the h is the depth of that partition, and that's a function. Goodness, my eye hurts. This hurts. I've got conjunctivitis in this eye, and it just is driving me crazy right now. It just happened overnight. I didn't have it going to bed, but this morning I woke up with it. I'm trying to think why. Okay, I got it. The y is a division of the plate. Okay, and the plate is submerged somewhere, so the how deep it is into the fluid depends on the y along the plate. Okay, because if it starts, and this one starting from y is equal to c at the top, and y is equal to d at the bottom, so the y is something between C and D. So the depth of that y at any given y, that's what's a function of y. The length of that strip, especially if this was an unusually shaped thing, that could be a function of y too. And then the delta y is your thickness. So this is your depth times the length times the thickness. Multiply that by weight density, which is weight per unit volume. There's your length, width, and depth. So that gives you everything you need to know to calculate that weight density. Well, because this is the limit as your partition is going to 0 of this is your integral going from C to D. C is the upper and D is the lower. That's a little backwards feeling here. Times the depth function times the length function times the delta dy. Okay, so C and D are measured in y. Where h of y is the depth of the fluid at position y on your plate. L of y is the horizontal length of the position at that. Now, if it's a uniform plate, a rectangular plate, this is going to be a constant. The L will not depend on the depth at all. Okay. This one's not a uniform plate. Okay. The vertical gate in a dam has the shape of an isosceles trapezoid. Now, what does isosceles mean?
Not right angles in the corners.
Okay. Basically, iso means same. So this is, when they say it's a trapezoid, that means it's not a rectangle, and yeah, your angles are not the same. But isosceles trapezoid means the two opposite sides are, even though they're different directions, they're same length, and these are parallel. So this is what they mean by isosceles. Iso means same. The sides are the same on either side. So this is a gate that you have somewhere in the dam. You open it up, water comes rushing out and turning your turbines or whatever. Okay, if that's a hydroelectric dam. Okay. So it's an isosceles trapezoid, 8 feet across the top, 6 feet across at the bottom, height of 5 feet. So the deviation here and here, in other words, is 1 foot on this side and 1 foot on that side. Okay. What is the fluid force on the gate when the top of the gate is 4 feet below the surface of the water? All right. Okay. Now we got to do a couple of things here. You want your, let me do it here. Let's just take a representative strip here. And the thickness of this is going to be our dy, or delta y, or dy. Okay? Now, for that strip, the depth from the surface of the water to there is going to be your h of y. Okay? Now, y is going to vary from 4 to 9, right? Because you're dealing with a dy. The top of that gate is at 4 feet, and the bottom of the gate is another 5 feet down. So you're varying from 4 to 9. Okay? And the depth is going to be, okay, depth is just going to be y, I think. Okay? Because if you're starting at 4 here, that's the depth of 4. You're going down there to the depth of 9. So I think that function there, I think, is just 4. Let me make sure of that before I go any further. Oh, no. Okay. Yuck. I was saying it was going to be y. I said 4. I meant to say y. But rather than letting y go from top to bottom, they're using y. I don't know where they're measuring their y from. Oh, there it is. Okay, it is the top. So they put their axis here. Okay, so here y is equal to 0, and then it's going down. Here y is equal to 0. Here y is here y is equal to 0. So this is the horizontal axis here. Y is equal to 0, but the gate is from y is equal to 4 down to y is equal to 6. Okay, so the h of y. Now, that's how I would set it up. They're setting it up. No. If you let this be 0 here, then this is minus 4 here, and this is minus 6 here. So you're going from minus 4 to minus 6. Oh, minus 9. Sorry about that. Minus 4 to minus 9. I had it right before. But you see, by doing it their way, they're introducing all these negatives in here. And you just have to keep that straight. The depth of your thing is minus y. I was saying h of y was equal to y, but because you have the minus signs in there, it's minus y. Okay? Because it starts at minus 4 and goes down to minus 9. So that's your h of y. Now, you've got to figure out what that length is. The length from here to here. The width is delta y. What is the length here? Basically, use this little triangle here, or the little triangle here. It doesn't really matter which. You have an expression here, and this is what the length. By choosing the axis to be the center of the gate here, then your x here, this is x equal 4 here, and x equal 3 here. Okay? This is x equal, because half of 8 is that, and this is x equal 3 is there. Their drawing to me does not look like it's quite to scale, but maybe it is. Okay? Something like that. All right. Now, what is the length there? You can set up a little ratio here, and I think that's what they do. And it's basically your this is the length you're interested in, and we're going to double that, okay? But let's just do one side to begin with, okay? I know they do them both. Why would they want to do them both? But let's not. Okay. No, they say the right side of the gate, so they're just going to do this one. Okay. Now, they're taking a point right down here and a point right up here. Okay? And we're going to find that the line that is described by, and that's going to be the x value of this is going to be the length of that. Okay? So they do y minus, and down here it's a minus 9. So this is sort of your point slope formula in some sense? No. Yeah. Yeah. That's equal to your slope, and the slope here is, and again, they're using the whole thing, not half a thing. I would. Okay. The y value here is the change of y is 5. I don't know why they set it up this way. It looks like to me the easiest way to do this, remember this is 1 unit here. You have a change of height, in other words, your delta y is 5 and your delta x is 1. Okay, that's the slope. Okay, so 5 over 1, or 5. That's the slope of that line there. Times x minus 3. Okay? And that basically is what they do here. Y plus 9 is equal to 5 times x minus 3. To me, the hardest part of these problems is always finding out this length function. It's a fairly simple process, but it's always so convoluted, you know. The calculus is easy once you have this done. So the this would be y plus 9 is equal to 5x minus 15, then subtract 9 from both sides, and that would be y, well, my pen disappeared. Now the whole thing is disappearing. Do you need one of these now?
Yes, sir.
I thought I pulled this out. No, that's my master. I want to give you the master. I thought, why is it not stapled? All right. Now, the very last question is the one we're going, is the type of thing we're going, no. Yeah, it's the type of thing we're doing right now. So if you can't get to that one, watch the video and hopefully it'll be there.
Yes, sir.
Okay. Microsoft PowerPoint is not responding. This is so aggravating. It did this to me yesterday in my second class, the third class of the day. It just quit. It wouldn't open. It wouldn't open at all. Now, right in the middle of it, it's not responding. Now, I don't know what's wrong with Microsoft that it's doing this now. The PowerPoint just went nuts, and it did this kind of thing, just sat there and sat there and sat there, and I never could get it to do anything. Now, I don't know why it's doing it now. So let me try this. Yuck. Let's try this and see what happens.
See you on Monday.
Yeah, okay. Have a good weekend.
Yes, sir.
Aggravates me. All right. I don't even know where this is. There we go. So of course we've lost everything. Okay. Yuck. So what we had here, and now my pen's gone. Okay. If I can recall what we had y minus 9, no, plus 9 is equal to 5, times x plus 3. No, minus 3, wasn't it? Yeah, minus 3. Okay, so that'd be y is equal to 5x. This was 5x minus 15, and then subtract 9 from it, and you get 5x minus 24. That's what we get. So that's your y value. That's your... So that's not what we want, okay? We want it in terms of x, so why in the world they did that? So let's add 24 to both sides. So that gave us y plus 24 is equal to 5x, and then divide by 5. So x is equal to y plus 24 divided by 5. All right. Now, remember though, x is just this length, okay? Your strip is 2x, okay? So that's why, so the length is 2x, so you would have to double that. So 2x is equal, and that's the length function, is equal to 2/5 times y plus 24. All right. So there is your length. Okay, so let's go back and see what we've got. Remember, your h was your minus y. Okay, put everything in terms of negatives, making this -4, this -9. So your integral here was your weight density of water, which is the 62.4, and you're going to be integrating from -4 to -9. -9 to -4 from bottom to top. Okay, -9 to -4 of minus y, that's your depth, times, and let's go on and pull the 2/5 out front. So 2/5 will be here. Okay, we don't need that. And then do y plus 24. And then your dy, that's your last term. Okay. All right. I'm going to erase my h is equal to -y just because I need the space here. Maybe I'll write that somewhere else. Okay. So let's do this integration. Now, to me, it makes sense to go on and multiply 2 times 62.4 and divide it by 5, whatever that turns out being. I'm not going to deal with it, but if someone got a calculator, 2/5 of 62.4. Oh, my head hurts. Yeah. Do this, 0.4 times 62.4. That'll be the easiest way to do it. 0.4 times 62.4. 24.96? Is that what you said? Okay. Okay. Now we're going to do that, and going from -9 to -4. Okay, and we're going to multiply these together. That's going to be a minus y squared minus 24y. dy. So you know what I want to do? I want to take out that minus sign too. Put the minus sign here and make these pluses. Okay? Your integrals are going to take care of the minus part. So what's the so minus 24.96, and then what's the antiderivative of y squared? Y cubed over 3. Okay? Plus, and what's the antiderivative of 24y? 12y squared. It's 24y squared over 2, and 12 divided by 2 is 20. 24 divided by 2 is 12. Okay? Got it? Sorry, I'm skipping steps because I don't have much room. Okay, and we're going to evaluate this from -9 to -4. Okay, which is going to be a real pain in the neck, but we'll do it. So this is -24.96 times. Okay, whoa. You got a calculator, do the math here. -4 cubed is -64, if I'm not mistaken, divided by 3, plus 12 times 16. I'm going to let you figure out what that is, okay? Minus, when you put a -9 in here, that's going to be a plus 27 over 3. No. 81 times 9 is 729 divided by 3. Can anyone do that? 729 divided by 3, that would be 243. I think it's 243. Then it's going to be a minus when you subtract the next one in, 12 times 81. Okay. So if you got your calculator, this is where we'll do it. Okay. -64 divided by 3 plus 12 times 16. All that, you've already done it? Oh, you already did this one. Yeah, okay, right. Okay, plus 243 minus, and that was 12 times 81. I would need a calculator for this one. And when you get that answer, multiply it by -24.96. Anyone got it yet? Can't read that. It's -12 times 81. Something I would do right there. Put my in bracket. Frankly, if I was doing this more slowly, I would have done this minus that would be 12 times the difference of that. That would be a -65. So -12 times 65 plus that minus that, and then multiply that by -24.96. So whatever, however you want to do the calculations. Has anyone got it yet? Good. It's a pretty big number.
If I've done this right, it should be 13,960.96.
Okay, that's exactly what they got, or close to what they got in the book. 13,936 pounds. Pounds because you're dealing with the mass density of water as, not mass density, the weight density of water is 62.4 pounds per cubic foot. Everything else is in feet, so that gave you, so it's very large force, very large force. That is basically almost 7 tons of force, right? Because 2,000 pounds is a ton, and that's almost 7 tons. Better be a strong little gate down there. Okay. Quite a bit of force to pick it up. Okay. Good deal. That was example 2. And by the way, LarsonCalculus.com has an interactive version of that. You can see it a little bit better there. All right. How are we doing on time? Oh, wait. Setting up the mathematical model for your problem. I'm sorry, you're at liberty to locate the x and y axes in several different ways. A convenient approach is to let the y-axis bisect the gate and place the x-axis at the surface of the water. Okay, fine. Okay, so that's how we set it up. Now, so the depth of the water at the gate is minus y. Up here it's minus 4, down here it's minus 9. And the y is going from minus 9 to minus 4, so it's the opposite of that. So that's the depth of the water, is your minus y. Okay? Now, the length, find the equation of the line forming the right side of the gate. That's the one over there. Okay? Basically, they identify it this way. So if they put their axes here, this is 3 minus 9, this is 4 minus 4, because you see the x value here is 4, because this gate was 8 feet across here, 3 feet across here, so it's 4 feet here, minus 4 depth, 3 feet here, minus 9 depth. So those are the 2 points. Now let's take those 2 points and do the slope, the 2 point, point slope form. So y minus, and you pick either one of these. They happen to choose this point, not that. Doesn't matter, you could have chosen that point too. Y minus and minus 9 is equal to the slope of this, which would be minus 4 minus 9, that's a plus 5 over 4 minus 3. So that gave us a slope of 5. Okay? So y minus and minus 9, or y plus 9 is equal to 5 times x minus 3. Use that. So that's where they got that. And there it is. Y minus and minus 9 is equal to, and boy, that's right what they did, but it's so much easier just to look at it and say 5 times x minus 3. And then you multiply through that, and you get y is equal to 5x minus 24. But you don't want y as a function of x. You want x as a function of y, because you need that as a function of y to do your problem, since your dy is your increment. So turn that around and make it x is equal to y plus 24 divided by 5. Okay. Now, you can see the length of the gate is exactly twice that. You see, we were going from this figure here, where this was your x, okay? Using these 2 points, that's your x. But the width here is twice x, so 2x is what you need. So that's where you came up with the 2/5 times y plus 24. That's the length of that increment, okay? That little bar across there. So finally, integrating from -9 to -4, the force is equal to the weight density, which is 62.4, times the integral from c to d, minus 9 to minus 4. Your h was minus y. Your L was that thing we just did, 2/5 y plus 24. Okay. What I did, and they ultimately are going to do, is bring the 2/5 out here times the 62.4. They did it. And go from minus 9 to minus 4, and then when they multiply those together, they get a minus here. Pull the minus out and give them this, which is what we did. You get y squared plus 24y. And then when they do the integration of that, you get y squared over 3, which is what you've got, plus 12 y squared. And then you evaluate that there, and you come up with an thing. You did this, and did all that. That's your answer. Okay. And when you multiply those together, hopefully you'll get the same thing. It's not exactly equal to that. It should be approximately equal to 13,936 pounds. Okay. Now, that's the last slide in this section, but it's not the last problem in this section. So let's go back. How are we doing on time? It's what? We passed. Okay. All right. feel like I passed. Okay. We'll do example 3 next time. Sorry we didn't get it done this time. But let me go run off. Does anyone need to leave right now? I've got one copy of the test already run off. I'll have to go make the other 2 copies. And again, I apologize for not having them done. I had planned to do it yesterday and got hijacked by students, which is what my job is. So does anyone need this today? I mean, right now, need to leave? Who wants to go first? Huh? Okay.
Then you said you only had one left.
No, I was going to go make more copies.
Oh, I thought you were going to use the one.
No, I just said, who needs to leave first? Because I've got one copy.
Oh, I don't need to leave.
Okay. Okay, well, whoever. Okay, so I need, can you take one to, okay, so you have 2 for you, so 4 copies. Okay. I'll be right back. One of these days. And is anyone else with this? Check my roll up and remind me to make a copy. I gave one to Clark, Vince, DeMarcus, Daniel. No, I gave one to Daniel. Oh, Charles. Okay. Vince, DeMarcus, Charles, Catherine, and Jordan. So 5 copies.
We'll see you.
All right. Take care. Have a good weekend.
You guys have a good one. Thanks.
Sorry, I just realized it says test 1 at the top. It's supposed to say test 3. Because we've done 2 tests, right? We're working on the second one.
Yes.
So you change that to 3. Okay. Sorry, the copier I went to was the strictest and fastest to get to, so it didn't have statements. All right, thanks. Sorry. That was a rush job. What's that?
Didn't want to stop the recording.
Yeah, I meant to stop before I left, and I didn't.